Welcome to the Red Hat AI Day of Learning. In this talk, James, Philip, and myself are going to talk about the three different practical ways for an organization to really solve some of the challenges in scaling their internal AI infrastructure to meet the demands that they see. First, let's go through intros. My name is Will McGrath. I'm on the product marketing side for the AI business unit. James?
Hey, I'm James Harmison. I'm a technical marketing manager in Red Hat's AI business unit.
And Philip?
Yeah, so I'm Philip Hayes. I'm an AI architect, also in the Red Hat AI business unit.
Great. So the structure of the presentation, it'll be pretty simple. I'm the marketing guy, so I'll do the intros for it. And then both James and Philip will dive into a little bit more technical examples and provide a couple of demos. All right, so first let's take a look at some of the challenges. In implementing generative AI, there's a number of challenges that customers face in moving from PCs and POCs to production. We believe some of the challenges include things like cost, where customers are really struggling to run large proprietary generative AI models and services, especially as they scale the amount of AI applications that they want to bring to production. That's the training, the tuning, and running those models at scale. Second one is around control. Customers really struggle with gaining control of the usage of some of the common generative AI models while still encouraging innovation and experimentation. They don't want to really set this up in a way that there's a bunch of shadow IT that goes on with customer. If they're internal customers that are data practitioners need to access some of these models and the resources required for it, like things like GPUs. And then finally, the scale. Similar to control, when you actually go to deploy the models, how do you actually do that cost effectively? Doing it for 1 or 2 models is fine. You can kind of find ways to get it deployed, but as you actually implement more, into the tens or dozens of models, the challenges become larger and larger, especially as the number of the higher parameter models as you try to scale that. So we're going to talk through 3 different customer approaches here. There are going to be 3 different topics. One for cost. We'll discuss GPUs as a service as a way of implementing your own on-demand GPU infrastructure within your environment. Second is for control. We'll actually talk about the concept of models as a service. And finally, for scale, we'll talk about one of the most pressing challenges for scaling models, especially LLMs, and that's today is inferencing. And as I mentioned at the start, James and Philip and I will actually provide some technical demos as well. So let's take a look at the first one, optimizing GPUs. So when we look at GPU usage and some of the challenges for GPU usage, GPUs are really the linchpin for generative AI models. You can get by with CPUs for many predictive models, but GPUs, pretty much any generative AI model requires the use of GPUs at some point in time. A number of the challenges that you face here are access to GPUs, whether they're limited supply, some of the cloud constraints, some of the internal competition between some of the data scientists and AI engineers that want to access them. If you're actually providing access to data scientists or AI engineers, and you're not providing that access more freely, then they might turn to shadow IT, as I mentioned before. So using third-party services in an unsanctioned way can expose sensitive information or company information from the various cloud providers. The other challenge is resources for GPUs are often spread across cloud or on-prem, making access to those really challenging. And the management of those and the measurement of those, especially the resource allocation, really challenging. And then finally, one that I want to talk about is the difficulty of actually tracking that usage in return on investment and identifying underutilized resources. So all this kind of moves into an area that calls for looking at different ways of automating and optimizing the use of GPUs. One customer that I want to talk about that actually kind of helped solve that problem on their own is a company called Turkish Airlines. They have about 20 different data scientists, but over 200 application developers. Their use cases range from predictive to generative AI. About 50 of them or so that they're using. Then they're looking to combine that to generate about $100 million a year in either revenue increase or cost savings. Range from fuel consumption, water tank prediction, dynamic pricing. They were already a user of Red Hat's hybrid cloud platform, which is Red Hat OpenShift, but they were looking at ways to automate that into a working cluster with GPU and CPU resources without having to go through the expensive process of logging service tickets, waiting a couple hours to a day or two to actually get that environment set up for them, So they were looking at ways they can use OpenShift and OpenShift AI to dramatically decrease the time it took to create workspaces and GPUs. They decreased it from a matter of hours to minutes. Now I'm going to hand it over to James, who's going to demonstrate an approach to a type of GPU as a service infrastructure.
Hey, so I'm James, and what I have here, I have an environment where I'm running the latest stable release of OpenShift, version 4.19. And in my deployment of OpenShift, I'm simulating a small portion of a customer's AI environment. I'm running in the cloud right now. So in the cluster that I'm currently in Amazon, you can see that I have a few different instances of type G4DN and G6E, where G4DN instance types come with an NVIDIA T4 GPU for acceleration of AI workloads, and the G6E instances come with an NVIDIA L40S accelerator. Even though they're both 2x large, you can see that the memory allocation between them is different. So I have some sort of heterogeneous pool of accelerated compute that I need to be able to manage for multiple developers doing different kinds of work. I do want to call out that this architecture would work just as well if we were talking about bare metal with GPUs and physical servers. It would also work just as well if I were using techniques such as MIG or time slicing for logical segmentation of GPU resources. But today, I'm just going to work with these instance types on Amazon. As a cluster administrator, you can see I'm signed into my own personal account here. And on my account on this cluster, I was able to define a couple of different types of policy resources to ensure that my data scientists had access to what they need. The first example I want to talk about is the cluster queue. This is coming from the Red Hat build of Queue Operator, which is integrated into OpenShift AI for workloads. Our cluster queue resources define not only the types of resources and the sharing behavior and the priority and preemption behavior for these resources, but also defines quotas. So in this case, because I have two instances with NVIDIA L40S GPUs, I said that my cluster queue could have at maximum 2 of these GPUs in use. The queue for the NVIDIA T4 instance types is similar and just references a slightly different flavor. Those resource flavors include things such as taints and toleration configurations, as well as node selectors that I'm able to use to differentiate between my two instance types for these cluster queues. Additionally, as an administrator, I defined hardware profiles, which are an OpenShift AI feature that integrates with Queue. My hardware profiles come in 3 flavors. I have one that allows generic CPU and memory. These hardware profiles are intended on a per workload basis rather than the entire cluster. And I have 2 other hardware profiles, one each for my L40S and T4 GPUs. So as an administrator, I know that this cluster has 4 nodes with GPUs. Each of them has 1 GPU apiece. This means that one workload can't use more than 1 GPU. So I was able to define the hardware profile policy to ensure that my developers got what they needed. Additionally, as an administrator, you can see that I have administrative access to the entire OpenShift AI dashboard. I'm able to configure cluster settings, things like that. And one other aspect that I wanted to bring up was to talk a little bit about the NVIDIA DCGM dashboards. These are provided by NVIDIA, and these dashboards provide a high-level view of how the hardware in my cluster is being utilized. Everything from temperature to power utilization to even clock speed to show which GPUs are busy, and utilization, showing which ones are actively performing work. Right now, my cluster is pretty quiet. I have a scenario where I have 2 different users who are doing very different kinds of workloads, so we're going to explore them one at a time. On the left, I have my Project 1 user. My Project 1 user has access, first off, only read-only access to the OpenShift data science applications, or the place where we keep a bunch of shared resources in OpenShift AI, but they also have read-write access to Project 1. Our other user, Project 2 user, has access to Project 2 similarly. These resources views are showing what's available in their current workspaces. The amount of resources they've been delegated is impacting all of this. You can take a look at the generic OpenShift pods that are running for each of these users. Oh, this user was checking out his local queue a moment ago. So this guy has access, or has currently running a Workbench and a Qwen 3 model running in OpenShift AI model serving. This guy has a Workbench up for training. If we look at what we can see in their data science projects through the OpenShift AI interface now, you can see that Project 1 user has a single Workbench up and a single model deployed, and our Project 2 user just has that Workbench up in his project right now. Interacting with this Workbench, this is sort of a mock scenario. These aren't the kinds of work, this isn't the exact work that I would expect these users to be running, but it shows a good amount of information about how the GPUs are being used at least. So for my Project 1 user, you can see that he's running a simple UI in a Jupyter notebook. to interact with the language model. So we can run that code. And then the user is able to chat with the model that we have running and get simple responses directly. Because I'm using the Qwen 3 model, this model is a reasoning model, and we have all the reasoning tokens being output as well. So we can see everything that the model is doing here. You can imagine that in real life, this user might be performing operations on MCP servers and building an agentic application, doing some prompt engineering to ensure that he has an agent that's able to integrate into an application and performing as expected. But this simple example works just fine. To show off what those hardware profiles look like from the perspective of the user, first off, all these things take place at the API level, but they're demonstrated for us inside the user interface as well. So it's simplest to see in this self-service mode, the policy that's been defined for this user is that he's allowed to use 2 of the NVIDIA L40S accelerators. So we can deploy a second model and see in the UI that he has the choice of trying to deploy on CPU only, which won't work so well for a generative AI model. Or he can say, I'm going to use my NVIDIA L40S. He doesn't even see the access to the T4. And we already have a model prepped and ready to go. We can deploy this model pretty quickly. It schedules. We can see the pod start to come up on the node. So one user in a generative AI workspace, able to operate on resources that have been allocated to him, and able to do everything he needs to do pretty quickly and easily in the self-service interface. The other user is doing a very different kind of work. This user is doing a bit of distributed training. The particular training jobs that I have configured here are mostly for example, just to show the workloads being scheduled. This one, for example, uses the MNIST fashion data set, and the MNIST fashion data set allows you to categorize items of clothing from small pictures. So he's training a neural network, and he's doing so. Actually, we're going to need to grab a new key, so I'm going to do that real quick. This one, we will invalidate this key very shortly just to make sure that it doesn't end up on the stream. But in the meantime, this user grabs his token and authorizes as himself to run these workbenches, these training jobs. And go. So the first job schedules this job to be running across multiple GPUs, across multiple nodes. He's configured that he wants 1 GPU per node, and he wants 2 workers for this job, for this MNIST fashion training job. The job takes a little while to spin up as it goes through the admission process, ensures that he has all of the quota that he needs. And we can see that the pods will be starting up here very shortly as soon as the workload comes up. I showed earlier the local queue. And this is a place where, at the API level currently, any user is able to come and look at what resources they've been allocated, how they're consuming them, and how they're behaving. We can see that we have 2 pending workloads with 1 reserved. Our 1 reserved is our workbench. We've got an update. And now I see I have 2 reserved workloads with 1 pending. So we saw that we just went through the admission process. The quota was granted. His pods are running. And if we come over here, we can see that the job is waiting to complete as it does the training on the MNIST fashion data set now. Additionally, I did schedule both of these jobs to run at once. So this second job also requires 1 GPU per node and has 2 workers. We can see that it was still sitting in that pending state in the local queue, and the pods for the second run are going to stay in that pending state, not admitted, until the GPU resources have been released by his other training job. At the same time, if we look at our Project 1 user, he's still able to chat with the language model that's running on the GPUs that he had reserved. Do you know any good recipes? And all of those resources are working exactly as the data scientists need. He can continue his agentic development or his prompt engineering or whatever data science task he was performing in this namespace. And finally, to clean it all up, we can see, hey, those GPUs are doing some work now. They're doing inference work. They're doing training work. We're able to see the activity show up right away. And if we come to our cluster queues, we can, at the API level, continue to see the utilization of those resources. Right now, we have 1 pending and 2 reserve workloads on those T4 instances for that training job. We saw how much CPU and memory was being used. We had an update. I suppose our MNIST fashion training finished, and the other job is running now. All of this is visible to the administrator. Additionally, more capabilities are going to be coming across the lifecycle of Red Hat AI 3.0. So additional UIs to improve the user visibility into their queues and their consumption. Additional UIs for administrators to view the overall cluster-wide utilization. Newer capabilities such as multi-queue work and integration with advanced cluster management for Kubernetes to include multiple clusters worth of GPUs and management of those resources. And we'll have more to show you about cohorts and resource borrowing coming up in the future as well. All right, And with that, head back to Will. Thanks.
Excellent. Great demo. Thanks, James. So the second area that we're going to talk about is a concept called models as a service. If you want to share the screen again, James, we can talk through a little bit about what that actually entails. So looking at throwing GPUs at a problem, as James kind of talked through, can be pretty expensive. For many organizations, they're using Pioneer models, but they may not be ideal in all situations, whether they want smaller models that can be custom trained or optimized, whether it's for costs or compliancy or data sovereignty. Many platform engineering and IT companies groups are actually investing in adopting open source models like GPT-OSS or Llama or Mistral or DeepSeek and others. But implementing entirely within an organization can be challenging. How do you actually prioritize those GPUs? How are they being used? There's a lot of downtime where GPUs aren't even being used and people are waiting for their own GPU. So the duplication of GPU resources and underutilization can be a challenge. And developers that are using Gen AI models may not be the best people to actually choose which model is best, which one knows the types of skills and knowledge that they need for that particular use case. So that becomes a challenge as well. So the concept of models as a service is something that Red Hat itself is actually implemented. This one within Red Hat, if you go to the next slide, thanks, James. The customer use cases really came from the idea of getting repeated access or requests from our AI business unit for internal consumers. Red Hat has over 19,000 employees. You can imagine generative AI is the biggest thing that people want to play with. And so the requests kept on coming, and we started off granting GPUs to our own internal clusters to folks to experiment with and have a sandbox development environment. But after several requests and months of trying to handle this, the requests became overwhelming. So we looked at things like quotas and auto scaling and MIG for GPU slicing, but they were all thrown out. So what we did is we worked on taking back the GPUs, deploying a model once and putting an AI API gateway in front of it. In essence, we provided our own internal models as a service. And this actually helps control the costs, and we could actually provide chargebacks, though at Red Hat we don't do that, to kind of show, chargeback to organizations that are using the most resources. And that's kind of an example of how you as an organization kind of set this up internally. So I'll turn it back over to James to share a little bit more details from a technical aspect on that concept of models as a service.
Yeah, so one of the key things that we found is that the majority of language model use cases tend to be over an API. For instance, Red Hat AI Inference Server exposes an OpenAI compatible API endpoint for you to integrate with your applications. It's really common for agentic frameworks like LangChain to integrate directly into that API endpoint. And it's also really common for organizations to already have an API gateway solution somewhere within their organization. If you have an API-driven application, using an API gateway is a great way to control access to things like chargeback, as well as quotas, and ensuring that you're getting the proper level of service that you're expecting for different internal tenants. So most of these API gateways have become a bit smarter in the era of Gen AI and have implemented a way to do things such as token-aware backends and resolution for those. So first off, if you have a solution that you prefer for API gateways, Red Hat has proven out this pattern where the API gateway is a bit more modular, and we can just plug it in to the existing Red Hat AI platform overall implementation of model serving so that API endpoint can be token aware, and we can do chargeback by token. Additionally, coming in the Red Hat AI 3.0 lifecycle, we're going to have an opinionated solution if you don't have an API gateway or don't want to reuse your API gateway for this purpose. To be able to bring the API gateway directly adjacent to the model inside your cluster and make it as easy as possible to begin to get Gen AI level visibility into the access and utilization of your internal tenants. This is really about up-leveling and moving from bringing my GPUs as a service, where I'm making the GPUs available for people who are using them however they see fit, and more about bringing an API endpoint that they can begin to do integration with things like RAG applications, Raft implementations, where we're doing fine-tuning with inline retrieval, synthetic data generation use cases, agentic architectures. If you have the need for an API-driven LLM, and you need the way to control access for those internal tenants, this models as a service pattern is one that we have these opinions on, and we're about to have an easy button solution for you to deploy on your own clusters as well.
Excellent. Thanks, James. And then the final approach that we're looking at, or suggestion or for best practices, is around scale. When we talk about scaling infrastructure, in this case, we're going to actually focus on one aspect of that challenge, and that's the inferencing portion of the AI lifecycle, running the models in production. Managing the cost of inferencing, it can be challenging, especially given the different types of model sizes. There's a fleet of open source models that that can be used inside an organization that can actually increase as different data scientists and AI engineers are selecting different ones for their own use case. There are many challenges, especially for the inferencing side. And what we've kind of centered on is VLM as a way to provide the performance to meet the capabilities of actually running those models in production without sacrificing accuracy. We need to select the right powerful inference runtime, and VLM seems to have become the standard that's out there. And the other thing to consider is really the support for AI accelerators. VLM actually provides the most broad use of different types of AI accelerators today. NVIDIA seems to be the dominant vendor, but supporting other vendors' accelerators is a real key decision for future usage. What we've done within Red Hat is we've taken the most common Gen AI LLM models, your llamas and DeepSeeks and Qwens and Mistrals of the world, and applied compression techniques to VLM that actually can reduce the number of GPUs that are required to run those models in production, often by 2 or 3-fold, while maintaining 95 to 99% of the accuracy. I'll explain one quick customer use case because I want to give some time for Philip to kind of talk through some of the improvements here. But one is a use case is a North American bank that was looking at reducing the complexity while increasing the performance of several llama and whisper types of models. And they were looking to do this on premise for safety and operational reasons. They approached Red Hat, who described to them the whole investment that we have made in VLM and the model optimizations that we've done. And they were excited about being able to kind of containerize some of these standard models to help with data privacy and security. They were even more excited about the future of AI inferencing at scale through a recent open source community project called llm-d. I'm going to turn it over to Philip to talk more about llm-d and give a quick demo.
Thanks, Will. Yeah, so as Will mentioned, I'm going to just talk briefly about llm-d. So llm-d really is designed to solve the problem of distributed inference. So, if you think about the world of API-based services and microservices, it's a well-solved problem at this point how to scale those services, especially with platforms like OpenShift, where you can horizontally scale multiple instances of your services, and generally they're stateless, so they're getting requests in, they're accessing a database or a cache and responding. That for that idea to work, with inference, there's a different set of challenges. So the idea is, again, we want to be able to scale our inference pods. So our pods running in OpenShift, running VLM, serving these models. We want to be able to horizontally scale these, but we want to do this in an intelligent manner. And, again, one of the challenges would be that when you first send in, a large context into a model, there's work that needs to be done in order to initially pre-fill that the cache to basically translate that prompt, that context into the tokens and store that in cache, and then to be able to start then responding. That's a very, very compute heavy task. And the idea is that if you send in a second request, you want to make sure that you're not repeating that work. You want to go back to the pod that's previously done that work. So that's just one example. Another example of where we're focusing with llm-d is to be able to sort of split those workloads between the pre-fill stage and the decode stage. They have different requirements around resources, around compute and memory, so it makes sense to configure those on nodes more suitable for those kind of workloads. So with those kind of techniques, we can intelligently distribute multiple instances of the same model and provide much better performance across all of those instances. So let me just give you an example. One kind of simple example to demonstrate is prefix cache aware routing, where we're basically routing requests back to the same pod that has already dealt with that previously, as I explained, so we don't have to do that pre-fill stage again. So if you look at my OpenShift instance here, you can see I've got 2 instances of the model. Oh, we need to share my screen now. Thank you. Let me do that. Let me share the entire screen. There we go. Okay, so you can see I've got 2 instances of the same model running here. 2 instances of llm-d running. They're both consuming a GPU each. And in front of those, we have a service which has got an ingress, so we can basically hit the service using our client. In this case, we're using anything LLM to start, talking to these models. And the service is going to generally round robin these messages across the models until it starts to, notice that we've got, large context we've already processed on a particular model. It's going to route it to that one rather than just using round robin. So the other thing I've got, set up as well is a simple kind of dashboard showing standard things like time to first token, which is a common metric with large language models, inter-token latency. But more importantly, for this example, we can show when the KV cache is hit on a particular pod. So I'm going to show just again with anything LLM here. If I just ask in a simple message, tell me a joke, for example, I can spell that. We'll see here now that we're going to start getting some data in here up here. We've got a request came in, but we haven't hit the KV cache because this context hasn't been seen again. But also it's configured to only really start activating after about 200 tokens. So once we get a sequence of 200 tokens that matches a previously processed prompt, then we'll route that back to that previous pod. So if I start sort of building this up now and say, okay, tell me a story. Because of the way that large language models work, every time I send a prompt back to my model, it's sending all the previous messages as the context. So it's effectively a stateful conversation with that model. So you can see we're still not hitting the cache. But if I start building this up now and say summarize this, for example, the context is going to start building up bigger and bigger, and we're going to start hitting this KV cache in a few seconds as it starts to sort of recognize that context. So let me just try it again. Just to try, I'm just getting it to sort of build up the text here. So we should start to see the KV cache being hit. There we go. So we're now seeing it now that this part now, this is giving us the percentage of requests that are hitting that KV cache. So if I again tell it to just repeat that last thing to try and make it longer, it's going to hit this same part again. It's going to be routed in. You can see that's gone up now to 23% on that part. So oh no, sorry, 33% on that part. So you can see that it's starting to intelligently route messages back to a particular part. Another example here would be, let's say I've got a large amount of text that I want to summarize, right? So I'm going to start a new thread and I'm going to say, summarize this. A very common task, right? This is about, I think, about 10,000 word or 5,000 word essay. So I've sent that in, right? Now, first thing we should see here is we should see the time to first token jumping up here, because we've just sent in a huge amount of text and it's going to be able to process that. It's doing that pre-fill stage. So you can see we've got a bit of a jump here now in the time to first token, which makes sense. Let me just ask it again to make that a bit shorter. Again, that will send in that whole context back. We should get a cache hit again because it will recognize that. Okay, so there we go. Got another cache hit. But we'll see here that the time to first token, though, will should start to reduce because it doesn't need to reprocess that cache every time. So we won't get those big hits that we got previously. So again, I can just hit that again. I'm just telling it to summarize it and make it slightly longer. And again, every time now it should hit this same part in order to do that. And you can see the time to first token is starting to come down now, as it doesn't need to keep reprocessing that prompt every time. So that's the idea. It's quite technical, but again, it's just about how clever can we be to be able to scale the same model in a distributed fashion and then be really intelligent about where we route our messages based on previous context, that kind of thing. So again, that's just one area that we're working on with llm-d. There's other areas as well, like the whole pre-fill and decode disaggregation. That may be something that we'll cover in a future demonstration. So there we go. Let me stop sharing my screen.
Yep.
Yeah.
And we're right at time. So Will, if you want to close this out.
Yeah, so here are some resources that you can actually access to. Hopefully, you'll be able to access these through this webinar system. But resources on GPU as a service, MAS models as a service, and llm-d. Thank you, Philip and James, for partnering with me on this presentation. I hope you learned something and look forward to talking to you in the future. Bye now.
Thanks all.
Thanks, everyone.